Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Pythagoras of Samos, a figure shrouded in enigma, emerges from the annals of history as a mathematician, philosopher and mystic. Separating historical fact from the elaborate tapestry of legend proves a formidable task. The very name evokes images of right triangles and profound mathematical truths, yet the man himself remains elusive, a composite of verifiable accomplishments and embellished narratives. Central to understanding Pythagoras is the concept of the Pythagorean brotherhood, or school. This was more than a simple academy. It represented a unique confluence of philosophical inquiry, mathematical exploration, and mystical beliefs. Within its secretive confines, knowledge was pursued as a path to spiritual purification, and discoveries were often attributed to the collective rather than individual members. This communal aspect presents a significant challenge to modern scholars attempting to disentangle Pythagoras's personal contributions from those of his disciples. The Pythagorean legacy extends across several key domains: number theory, geometry, music theory, and cosmology. Their explorations into the nature of numbers revealed profound relationships and patterns, shaping their understanding of the universe itself. Geometry, particularly the study of shapes and their properties, provided a visual language for expressing mathematical truths. Music theory, grounded in the mathematical ratios of harmonious intervals, offered a connection between the abstract world of numbers and the tangible realm of sensory experience. Cosmology, the study of the cosmos, sought to uncover the mathematical order underlying the celestial movements and the structure of the universe. This essay aims to explore Pythagoras's contributions to these fields, acknowledging the inherent difficulties in definitively attributing specific discoveries directly to him. The collective nature of Pythagorean thought, coupled with a scarcity of primary sources, necessitates a careful approach, one that considers both the historical context and the enduring influence of Pythagorean ideas. One of the primary obstacles in reconstructing Pythagoras's life and work lies in the absence of contemporary written accounts. The earliest sources date from centuries after his death, relying on oral traditions and the writings of later philosophers and historians. These accounts, often colored by hagiography and philosophical agendas, present a complex and sometimes contradictory picture of Pythagoras and his teachings. The very act of attributing specific discoveries to Pythagoras becomes problematic when considering the secretive nature of the Pythagorean school. Knowledge was carefully guarded, often transmitted orally, and attributed to the founder as a sign of respect and adherence to tradition. This practice obscures the individual contributions of other members and makes it difficult to ascertain the precise role Pythagoras played in the development of specific mathematical or philosophical concepts. The Pythagorean brotherhood functioned as a tightly knit community, bound by shared beliefs and a commitment to intellectual and spiritual growth. New initiates underwent rigorous training and were expected to adhere to strict rules of conduct, including dietary restrictions and a vow of secrecy. This communal lifestyle fostered a sense of shared identity and purpose, but it also blurred the lines of individual authorship. Discoveries were often presented as the collective wisdom of the school, reinforcing the authority of Pythagoras and perpetuating the tradition of anonymity. Pythagoras's journey began on the island of Samos, a vibrant center of Ionian culture in the 6th century BCE. Born around 570 BCE, he is said to have been a gifted student, excelling in mathematics, music, and philosophy. Driven by a thirst for knowledge, he embarked on extensive travels, seeking wisdom from various cultures and traditions. Accounts suggest he visited Egypt, where he studied mathematics and astronomy with Egyptian priests, and possibly even traveled to Babylon, where he encountered advanced mathematical knowledge. These travels exposed him to a wealth of ideas and perspectives, shaping his own philosophical and mathematical outlook. Around 530 BCE, Pythagoras migrated to Croton, a Greek colony in southern Italy. There he established his famous school, attracting a devoted following of disciples. Croton provided a fertile ground for the dissemination of Pythagorean ideas, and the school quickly gained influence in the local community. The Pythagoreans became involved in politics, advocating for ethical governance and social reform. Their influence, however, also aroused opposition, leading to eventual conflict and upheaval. The establishment of the Pythagorean school in Croton marked a turning point in the history of mathematics and philosophy. It was here that Pythagoras and his followers began to develop their unique blend of mathematical inquiry, philosophical speculation, and mystical beliefs. They saw numbers as the fundamental building blocks of reality, believing that the universe could be understood through mathematical relationships and ratios. This conviction fueled their exploration of number theory, geometry, and music theory, leading to groundbreaking discoveries and profound insights. The challenges in definitively attributing specific discoveries to Pythagoras himself stem from the very nature of the Pythagorean school. It was a collective, a brotherhood bound by secrecy and a shared commitment to knowledge. While Pythagoras undoubtedly served as the charismatic leader and guiding force, the contributions of his disciples cannot be discounted. The lack of contemporary written accounts further complicates the task of historical reconstruction, leaving scholars to rely on later sources that may be biased or incomplete. Despite these challenges, the enduring influence of Pythagorean thought is undeniable. Their ideas shaped the course of mathematics, philosophy, and science for centuries to come, leaving an indelible mark on Western civilization. Their emphasis on reason, order, and the mathematical structure of the universe continues to resonate with scientists and thinkers today. The Pythagorean worldview centered on the profound conviction that numbers constituted the fundamental building blocks of reality. They perceived the universe as an ordered cosmos, governed by mathematical relationships accessible through reason and observation. This perspective elevated numbers from mere tools for counting and measuring to the very essence of existence. Their explorations extended far beyond simple arithmetic, delving into the intricate properties and geometric representations of numbers, revealing what they believed were the underlying principles shaping the natural world. A cornerstone of Pythagorean mathematics lay in their study of figurate numbers. These numbers, represented geometrically by arrangements of dots forming specific shapes, provided a visual and intuitive understanding of numerical relationships. Triangular numbers formed by arranging dots in equilateral triangles began with 1, then 3, 6, 10, and so forth, each successive number adding another row to the triangle. Square numbers arranged in squares included 1, 4, 9, 16, and so on. Pentagonal numbers followed a similar pattern, creating pentagons with increasing numbers of dots. These geometric representations revealed inherent relationships between different types of numbers. For instance, adding two consecutive triangular numbers always yielded a square number. The visual demonstration of such relationships reinforced the Pythagorean belief in the interconnectedness of all things through numerical harmony. Figure-8 numbers were more than mere curiosities. They represented a tangible link between arithmetic and geometry, illustrating the profound order they perceived within the universe. Beyond figure-8 numbers, the Pythagoreans explored specific classes of numbers possessing unique properties that held symbolic and philosophical significance. Perfect numbers, such as 6, 1 plus 2 plus 3, and 28, 1 plus 2 plus 4, plus 7 plus 14, were defined as numbers equal to the sum of their proper divisors, those divisors excluding the number itself. These numbers were considered rare, and special, embodying a sense of completeness and harmony. Amicable numbers, pairs of numbers where each number is the sum of the proper divisors of the other, further exemplified the Pythagorean fascination with numerical relationships. 220 and 284 form the smallest pair of amicable numbers. The proper divisors of 220 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110 sum to 284, while the proper divisors of 284, 1, 2, 4, 71, and 142 sum to 220. These numbers were seen as representing friendship and mutual affection, reflecting the Pythagorean emphasis on community and interconnectedness. Certain numbers held particular significance due to their perceived sacred qualities. 10, in particular, was revered as the perfect number, representing the totality of the universe. The sum of the first four integers 1, 2, 3, and 4 equals 10, and these numbers were associated with fundamental geometric entities: the point, the line, the plane, and the solid. The Pythagoreans swore their oaths by the tetractes, a triangular figure consisting of 10 dots arranged in 4 rows, symbolizing the divine order of the cosmos. The Pythagorean belief in the absolute rationality of the universe, its complete explicability through whole numbers and their ratios, suffered a profound blow with the discovery of irrational numbers. This crisis, legendarily attributed to Hippasus of Metapontum, involved the realization that the square root of 2, the length of the hypotenuse of a right-angled isosceles triangle with sides of unit length, could not be expressed as a ratio of 2 integers. This discovery challenged the very foundation of their mathematical and philosophical system. The problem of irrational numbers posed a significant philosophical challenge. If the universe was fundamentally mathematical and numbers were inherently rational, the existence of irrational quantities threatened the order and harmony they perceived. The square root of 2, a seemingly simple geometric construct, defied explanation within their existing framework. This created a cognitive dissonance, forcing them to confront the limitations of their numerical worldview. The Pythagorean response to this crisis was unique. Rather than embracing the existence of irrational numbers and adapting their system accordingly, they reportedly attempted to suppress or deny their existence. Legend has it that Hippasus, for revealing this unsettling truth, met his demise at sea, either through drowning or banishment. While the veracity of this story remains debated, it reflects the severity with which the Pythagoreans viewed the threat posed by irrational numbers. This suppression, however, could not erase the mathematical reality. The discovery of irrational numbers had a lasting impact, forcing mathematicians to reconsider the nature of numbers and the foundations of geometry. While the Pythagoreans initially resisted this new knowledge, its eventual acceptance led to significant advancements in mathematics, paving the way for a more comprehensive understanding of the number system. The relationship between arithmetic and geometry held a central position in Pythagorean thought. They viewed these two branches of mathematics as intimately intertwined, each illuminating the other. Their study of figurate numbers exemplified this connection, demonstrating how geometric shapes could represent and reveal numerical relationships. The Pythagorean theorem, while predating Pythagoras himself, became a cornerstone of their geometric understanding, linking the lengths of the sides of a right triangle through a fundamental numerical relationship. The square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the other two sides. This theorem, expressed as a squared plus b squared equals c squared, provided a powerful tool for understanding geometric proportions and spatial relationships. It reinforced their belief in the inherent mathematical order governing the physical world. The theorem's applicability extended beyond abstract geometry, finding practical applications in surveying, construction, and navigation. The Pythagorean approach to arithmetic and geometry was characterized by a unique blend of intuition, observation, and deductive reasoning. They sought to uncover the underlying principles governing these mathematical domains, often relying on visual representations and geometric constructions to guide their explorations. Their emphasis on proof and logical deduction laid the foundation for the development of rigorous mathematical systems, while their initial resistance to irrational numbers highlights the limitations of their worldview. Their contributions to mathematics and their enduring belief in the mathematical structure of the universe had a profound and lasting impact on the development of Western thought. Their work established a framework for understanding the cosmos through the lens of numbers, a perspective that continues to influence scientific inquiry today. The exploration of numbers, ratios, and proportions by Pythagoras and his followers reached a crescendo with their groundbreaking investigations into the nature of musical harmony. This pursuit was far from a mere diversion. It represented a profound attempt to understand the underlying mathematical structure governing the universe, a structure they believed was reflected in the consonance and dissonance of musical sounds. The Pythagoreans recognized that certain combinations of tones sounded pleasing or consonant, while others were jarring or dissonant. The challenge lay in objectively defining these qualities. Prior to the Pythagoreans, musical understanding was largely subjective, based on personal preference and cultural tradition. The Pythagoreans sought a more fundamental basis, a way to ground musical harmony in the immutable laws of mathematics. Legend attributes the initial discovery to Pythagoras himself, supposedly overhearing the sounds of blacksmiths hammering at their forges. He noticed that hammers of different sizes produced distinct tones, and that certain combinations of these tones created particularly harmonious sounds. While the veracity of this anecdote remains debatable, it underscores the Pythagorean emphasis on empirical observation as a starting point for intellectual inquiry. Regardless of the precise origin, the Pythagoreans embarked on a series of experiments using stretched strings of varying lengths. They discovered a remarkable relationship between the lengths of the strings and the musical intervals they produced. Specifically, they found that simple integer ratios corresponded to consonant intervals. The most fundamental of these was the octave. When a string was exactly half the length of another, the shorter string produced a tone an octave higher than the longer string. This relationship was expressed by the ratio 2:1. Similarly, they discovered that a string 2/3 the length of another produced a musical fifth, a highly consonant interval represented by the ratio 3:2. A string 3/4 the length of another produced a perfect fourth, another consonant interval represented by the ratio 4:3. These discoveries were revolutionary. They demonstrated that musical harmony was not arbitrary, but rather governed by precise mathematical relationships. The beauty and pleasing quality of consonant intervals could be objectively defined by simple integer ratios. This provided a powerful new framework for understanding music, one that was grounded in reason and mathematical order. The implications of this discovery extended far beyond the realm of music. For the Pythagoreans, the fact that simple mathematical ratios underlay musical harmony was further evidence of the mathematical structure of the universe. It reinforced their belief that numbers were the fundamental building blocks of reality, and that the cosmos itself was governed by mathematical laws. The universe, they believed, was a harmonious whole, a cosmic symphony orchestrated by numbers. This led to the development of the concept of the music of the spheres. The Pythagoreans envisioned the celestial bodies, the sun, moon, and planets, as being arranged at distances corresponding to musical intervals. As these celestial bodies moved through space, they produced sounds, a cosmic harmony that was imperceptible to human ears, but nonetheless real. This music of the spheres was a reflection of the underlying mathematical order of the universe, a testament to the power and beauty of numbers. While the notion of celestial bodies literally producing sound may seem fanciful today, it is important to understand the philosophical significance of the music of the spheres. It represented an attempt to connect the microcosm of human experience, music, with the macrocosm of the universe. It was an expression of the Pythagorean belief that the same mathematical principles governed both the earthly and the celestial realms. The cosmos, in their view, was not a chaotic jumble of matter, but rather a beautifully ordered system governed by mathematical harmony. This harmony resonated throughout the universe, from the vibrations of a stretched string to the movements of the planets. The Pythagorean connection between music and the cosmos had a profound impact on Western thought. It influenced philosophers, scientists, and artists for centuries to come. The idea that the universe was governed by mathematical laws became a central tenet of Western science. The search for these laws, the attempt to understand the underlying mathematical structure of reality, continues to drive scientific inquiry today. The Pythagorean discoveries regarding musical harmony also had a lasting impact on the development of Western music theory. Their identification of simple integer ratios as the basis of consonance and dissonance laid the foundation for the development of scales, chords, and harmonic progressions. The concept of a musical system, a coherent framework for organizing musical sounds, owes much to the Pythagorean emphasis on mathematical order. The Pythagorean tuning system, based on the ratios of 2:1, 3:2, and 4:3, became the dominant system in Western music for centuries. While it had certain limitations, particularly when it came to playing in different keys, it provided a remarkably stable and consonant sound. The Pythagorean system emphasized the purity of the perfect fifth, which was considered the most consonant interval after the octave. The legacy of the Pythagorean tuning system can still be heard in modern music. While modern equal temperament tuning, which divides the octave into 12 equal semitones, has largely replaced Pythagorean tuning, the influence of the Pythagorean system is undeniable. Equal temperament represents a compromise, a way to allow music to be played in any key without sounding excessively dissonant. However, this comes at the expense of the purity of the perfect fifth, which is slightly out of tune in equal temperament. Some musicians and music theorists continue to advocate for the use of Pythagorean tuning or other just intonation systems which are based on pure integer ratios. They argue that these systems produce a richer, more consonant sound than equal temperament. The debate over tuning systems continues to this day, a testament to the enduring influence of the Pythagorean discoveries regarding musical harmony. The Pythagorean approach to music was innovative in its use of numbers to understand and explain musical phenomena. Prior to the Pythagoreans, music was largely understood through subjective experience and cultural tradition. The Pythagoreans brought a new level of objectivity to the study of music, demonstrating that musical harmony could be grounded in mathematical principles. This represented a significant shift in perspective, one that paved the way for the development of a more scientific approach to music theory. The Pythagorean emphasis on the mathematical structure of music also had implications for the way music was composed and performed. It encouraged musicians to think about music in terms of ratios, proportions, and mathematical relationships. This led to the development of new musical forms and techniques, ones that were based on mathematical principles. The legacy of this approach can be seen in the works of composers throughout Western history, from the medieval polyphonists to the modern minimalists. The Pythagorean exploration of music exemplifies their broader philosophical and scientific approach. They sought to understand the world through the lens of mathematics, believing that numbers held the key to unlocking the secrets of the universe. Their discoveries regarding musical harmony provided compelling evidence for this belief, demonstrating that even something as seemingly subjective as musical taste could be grounded in objective mathematical principles. This conviction shaped their understanding of the cosmos, their approach to mathematics, and their enduring legacy on Western thought. The Pythagorean exploration of music extended beyond mere acoustic observation. It culminated in a profound statement about the inherent mathematical structure of reality. This mathematical structure found perhaps its most famous expression in the Pythagorean theorem, a cornerstone of geometry. The theorem states that in a right-angled triangle, the square of the length of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the lengths of the other two sides. Expressed algebraically, this is a squared plus b squared equals c squared. While the theorem itself was known to earlier civilizations, including the Babylonians and Egyptians, the Pythagoreans are credited with providing a general proof. This proof, or perhaps a family of proofs attributed to the school, demonstrated the theorem's validity for all right-angled triangles, establishing it as a fundamental principle of geometry. One particularly elegant proof involves dissecting two identical squares, each containing four identical right-angled triangles. In one square, the triangles are arranged to leave a square with side length c exposed in the center. In the other, the triangles are arranged to leave two squares exposed, one with side length and the other with side length bis. Since the area of the original squares is the same, the area of the square with side c must equal the sum of the areas of the squares with sides s and bis, thus demonstrating the theorem. The impact of the Pythagorean theorem on geometry is immeasurable. It provides a fundamental relationship between the sides of a right-angled triangle, enabling the calculation of unknown lengths and areas. This has profound implications for surveying, construction, and navigation. For instance, builders could use the theorem to ensure that corners were perfectly square, a crucial requirement for stable and aesthetically pleasing structures. Surveyors could calculate distances and areas of land, even when direct measurement was impossible. The theorem also provides a basis for trigonometry, the branch of mathematics that deals with the relationships between the angles and sides of triangles. Trigonometry is essential for a wide range of applications, from astronomy to engineering. The practical applications of the Pythagorean theorem in the time of Pythagoras were significant. Land division, construction of temples and public buildings, and even the design of siege weaponry all benefited from a precise understanding of right angles and distances. The theorem offered a reliable method for establishing perpendicular lines, something that was essential for laying out fields, constructing foundations, and ensuring the stability of walls. It is reasonable to assume that Pythagorean mastery of this theorem gave them an edge in engineering and construction projects. It facilitated the creation of more accurate plans, more stable structures, and more efficient use of materials. Beyond its practical utility, the Pythagorean theorem held a deep philosophical significance for the school. It represented another example of the underlying mathematical order of the universe. The relationship between the sides of a right-angled triangle was not arbitrary, but rather a fixed and immutable law, discoverable through reason and proof. This reinforced their belief that numbers were the fundamental building blocks of reality, and that mathematics provided the key to understanding the cosmos. This conviction extended to their model of the cosmos. The Pythagoreans developed a cosmology that placed numbers at the center of the universe. While the precise details of their model remain debated, it is generally believed that they envisioned a universe governed by mathematical harmony. The question of whether the Pythagoreans were geocentric or heliocentric is a complex one. Some scholars argue that Pythagoreans himself may have proposed a proto-heliocentric model, with the Earth and other planets revolving around a central fire, rather than the Earth being at the center. Others maintain that the Pythagorean school was primarily geocentric, with the sun, moon, and planets revolving around the Earth. Regardless of the specific arrangement, the Pythagoreans believed that the celestial bodies were arranged according to mathematical ratios, and that their movements produced a kind of cosmic music, the music of the spheres. This concept of cosmic harmony was directly related to their understanding of music. They believed that the same mathematical ratios that governed musical intervals also governed the distances between the planets. Just as harmonious musical intervals were pleasing to the ear, the harmonious arrangement of the cosmos was pleasing to the divine intelligence that created it. This idea, while seemingly mystical, represented a profound attempt to unify the earthly and the celestial realms through the language of mathematics. The Pythagorean worldview, therefore, was a synthesis of mathematics, music, and cosmology. They saw these three disciplines as intimately connected, each revealing a different facet of the underlying mathematical order of the universe. Their discoveries in music provided empirical evidence for this order, while their mathematical theories provided a framework for understanding the cosmos. This holistic approach to knowledge was a defining characteristic of the Pythagorean school and had a lasting impact on Western thought. The legacy of Pythagoras and his followers is a complex one, fraught with challenges in separating the contributions of the founder from those of his disciples. The secretive nature of the Pythagorean brotherhood and the communal nature of their work make it difficult to attribute specific discoveries to individual members. However, the enduring impact of Pythagorean thought on Western science, mathematics, and philosophy is undeniable. Their emphasis on the importance of mathematics as a tool for understanding the natural world laid the foundation for the scientific revolution. Their development of geometry provided a framework for spatial reasoning and measurement that continues to be used today. Their exploration of music theory paved the way for the development of Western musical notation and harmony. Their philosophical ideas, particularly their belief in the immortality of the soul and the importance of living a virtuous life, influenced Plato and subsequent generations of philosophers. The unique blend of mysticism and rational inquiry that characterized Pythagoreanism is perhaps its most enduring legacy. They sought to understand the universe through both reason and intuition, combining mathematical rigor with spiritual insight. This combination, while sometimes viewed as contradictory, proved to be a powerful force for intellectual innovation. It allowed them to explore new ideas, challenge existing assumptions, and develop a worldview that was both intellectually stimulating and spiritually fulfilling. In conclusion, the Pythagorean school stands as a pivotal force in the development of Western thought. Their impact extends far beyond the realm of mathematics, influencing our understanding of music, cosmology, and philosophy. They championed the idea that the universe is governed by mathematical principles, a concept that continues to shape scientific inquiry today. The Pythagoreans demonstrated the power of mathematics to unlock the secrets of the cosmos, establishing a profound relationship between the abstract world of numbers and the tangible world around us. Their dedication to both rational inquiry and spiritual insight offers a lasting perspective on the interconnectedness of knowledge and the enduring quest to understand our place in the universe. The echoes of their ideas resonate throughout history, reminding us that the pursuit of knowledge is a harmonious blend of reason, intuition, and a deep appreciation for the beauty and order of the natural world. We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.